What's up, appliance technicians? This is Dan over at ApplianceTechAcademy.org. In today's training, we're going to be talking about adaptive defrost systems on refrigeration. And basically, what adaptive defrost systems are is they use logic processes to determine when and how long a defrost cycle runs. Now, these are really interesting because of the logic being used, and once you take some time, look through a wire diagram, which we're going to do in this training, you kind of understand how the system works, and you can kind of figure out where some failure points are. So, in this training, we're going over the basics of adaptive defrost, and we're just shortening that down to ADC. We're going to look at some schematics on how the control system works, and we're going to look at some basic diagnostics on it. And right here, this is just an old style defrost control. You can see you've got your wire connectors here. Got a little relay. That's going to be your little computer board. Takes all the inputs and makes some decisions. So let's dive in and see what we can figure out. So let's start with the basics. You got the defrost system. On most units or older units, it's going to consist of a bimetal, defrost heater, or some thermistors. Now, systematically, the cooling shuts off and the heater is energized, and that's to melt away all the frost buildup on the evaporator. As you can see here, we've got a pretty clear failure of a defrost system issue, and one indicator of that is, as you know, defrost elements typically are going to come down around here at the bottom. They're typically going to be at the bottom of it. Every once in a while, you're going to see them in the middle, depending on the style, but more often than not, they're at the bottom, and that's because heat rises. So we want the heat to rise up across the evaporator and melt all this away. Now, one indication in this picture, see how we got the heater around here and all of that's completely frosted up? That's a pretty good indicator that our defrost heater isn't working. Now, if we didn't have any frost here, that was all clear, and we just had this section up here where the suction line and the cap tube are coming in and they were frosted up, that'd be kind of pointing you towards more of a sealed system issue rather than a defrost issue. But you can see we've got a clear defrost issue here. Now, typically, you're not really going to be able to see it here, but generally you're probably going to have the bimetal over here. The wires come in for the heater, come up over there. So, and then that's probably, if I were to wager a guess, going to the evaporator fan. Kind of getting off track there, but basic defrost system right there for you. So the defrost heater, it comes in a variety of shapes and sizes. You've got one kind of like that, or your typical one like this, and then you got a bimetal. Basically, a defrost heater is just a resistive load. It produces heat when energized. So you would have line voltage coming in here, neutral connected over here. When we have both of those, they heat up. With defrost heaters, they're either on or off. They don't vary the heat output. It's not one of those things where if we give it 80 volts, it's going to put out less. In theory, that would work, but that's not how these systems are designed. Their sole purpose is just to remove the frost and ice buildup on the evaporator. Now let's talk about the defrost cycle itself. The defrost cycle removes frost buildup that occurs during normal operation. Some units are going to go based off a timed defrost cycle, maybe every 8 hours, 12 hours, 24 hours. It really depends. And then on units with adaptive defrost controls, the defrost cycle will vary based on a variety of factors. So depending on the model, it's going to look at how often the door is open, how long the door is open for, the compressor runtime, and then the length of the defrost cycle. And of course, on brand new units, there might be some more factors that play into that, but we're going over the basics here. So on newer units, the control boards are looking at a lot of factors. You can see we got a new control board here, and you got quite a bit going on. You got a little microprocessor there, a whole bunch of relays, a whole bunch of connection ports, and then you've got the older one there. So we're going to kind of look at both and take a look at a few things. On older units, as I was kind of saying, it's a bit more mechanical than it is with the newer units. The newer units are typically looking more at thermistors and sensory inputs, things like that. So on older units, to understand how the adaptive defrost system knows how long the defrost cycle is, we need to look at the schematic to understand how the system operates. And we want to see what the board is seeing or what it's using for its sensory inputs. Now, if you're looking at this wire diagram and it's a little confusing to you, no worries. It's, it kind of looks like some spaghetti thrown out there, and it can be a little difficult to understand unless you have someone kind of walking you through it or unless you're familiar with it. So we're going to go over the cooling circuit now. And what we're doing, we're just kind of reducing the problem. You'll hear me say this a lot in all the training. We want to reduce the problem. On this one, if we want to look at the cooling circuit, we don't need to worry about all these other lines and everything over here. We're just looking at how the compressor gets its line in neutral, how the condenser fan gets its line in neutral, and the evaporator fan. So on this configuration, when you got the thermostat right here, and this is what the user will turn, that little knob they'll turn to select their temperature, whether they want it warmer or colder, and then it closes. Our electronic control board sends 120 volts up through this line, which goes through the thermostat, and then it comes down and it connects to the evaporator fan motor, the compressor, and the condenser fan. So these three are in a parallel circuit. That means if one is energized, all the other ones should be energized. So it's a diagnostic approach. If you're out on a service call and the compressor's not running, but your evaporator fan is and your condenser fan is, there's no need to check the board because we know we're getting the voltage and they should be working. With that being said, we're not really going into diagnostics too deep here. With that being said, you can kind of see that. Now, notice one other thing. See how when those are energized, we have this line right here, comes back to the control board? That's going to be our sensing line. When the thermostat is closed, we're getting 120 volts to those loads and back here. So when the control board's seeing 120 volts on this line, it knows the compressor should be running and it knows it's in cooling. Now, let's kind of look at the thermostat real quick before we dive in deeper. On this unit, the cold control or the thermostat, it's a mechanical switch. It opens and closes the contacts inside, and you can see just two wires going in. Same thing on our diagram right here. We'd have an orange wire coming in, red wire going out. It basically opens and closes contacts based on the temperature. And you've got this little temperature probe here. This device is going to typically sit up front when you open the door so you can adjust it. And then this probe snakes back into the compartment somewhere. That probe right there is reactive to temperatures. So if temperatures go up, it kind of reports back there. If I remember correctly, it's something about gases in here. Not really going to dive too deep into that here, but basically speaking, when you set it to the coldest temperature, there's going to be a little, I don't want to say plunger, but a little ramp in there that's going to put some pressure on something. So the pressure in the tube needs to work harder to get it to close. Anyways, getting off track there. Cats are running all over the place. Anyways, so basically that's how that works. It's just a simple open-close switch there, wired in series with that. So when the cooling circuit, when the temperatures are satisfied, that thermostat that we were just looking at, it opens the circuit. So the control board, it knows it's sending 120 volts out this line. It's looking for 120 volts there. When this opens, look at that. Neutral back feeds through these loads and all the way to there. So we no longer have 120 volts at this connection right here. So when the control sees 120 coming out here, 0 volts there, it knows that the temperatures are satisfied. And that's how it knows how long the compressor is running for. So it factors that in to when it's going to run the defrost cycle next. Now let's take a look at the defrost circuit. When the control decides it's time to defrost, it kind of shuts off voltage to the cooling circuit. No more 120 volts on this line going there. And then it sends 120 volts up to our defrost heater right here. Now this is the same thing, same process. 120, but sending 120 volts out. It comes up through this bimetal over here to the defrost heater. And of course, neutral's coming in on this side. And now our defrost heater is energized. But the other thing you're going to notice when we reduce the problem to just the defrost circuit, look at that. On the other side of the bimetal, not on this side, but on the other side, it also loops back and it comes right down to the control board. This right here is how the control is determining how long the defrost cycle is running for. When the defrost heater heats up, it fully steams out the evaporator, kind of like, let's go back to this first slide, or not, where'd it go? There. When that heats up, it heats up, the heat rises up. You've got your bimetal hanging out right over here, most likely on this one. Once all this is melted away, that bimetal is going to start warming up. When it warms up, it opens up. And basically, a bimetal is two dissimilar pieces of metal right in there. And when you have two dissimilar pieces of metal, metal bends when it's heated. So you have two dissimilar pieces of metal. When they're heated, they bend away from each other, and they open up the electrical circuit. And when they cool back down, they close. So when it opens up the circuit, once the whole defrost system is defrosted, look at that, it's the same thing that was happening with the cooling circuit in regard to the sensing line. The bimetal opens because it's heated up. We no longer get 120 volts coming back down to the electronic defrost control. And it sees that. Oh, excuse me. It sees that, and then it says, okay, defrost cycle is done. And what it's doing, because you got 120 out, 0 volts back in, it knows the bimetal is open. What it's doing is it's counting how long that bimetal was closed for. So if it was closed for, let's say, 3 minutes this time, and the next time it was closed for 10 minutes, that shows how long it takes for that defrost heater to fully clear up the evaporator. And the assumption is if it takes longer, there's more frost buildup. So when it comes down to the adaptive defrost logic, it's factoring in the compressor runtime, factors in the defrost runtime, things like that. So if the defrost cycle is short before the bimetal opens, the unit's going to extend the length before the next defrost. And think about it. If it takes 2 minutes to fully defrost an evaporator before that bimetal opens, that means there's not that much frost on there. So the system thinks, okay, we don't need to run as many defrosts. Now, on the other hand, if the defrost cycle is really long before the bimetal opens, it's going to reduce the time before the next defrost cycle. And again, if you think about it, if it's taking half an hour to 45 minutes to fully defrost an evaporator, there's a lot of buildup, so it's going to reduce that amount of time. Now, this isn't really regarding adaptive defrost so much, but it kind of is to a certain degree. And the same thing kind of applies when it comes down to the door switch for sensing. We can see line voltage comes in. We've got one light interlock switch here. When the door is open, look at that. Line voltage is supplied over here to the lights. Neutral's on that side. And also, look at that. Sensing lines coming over here to the board, letting the board know how long the door's open. And then, of course, you got another light switch there. I'm not really going to worry about that. And if you're ever looking at a diagram and you're not entirely sure, which position the switch is in for what, just use the power of deduction. We know that the lights inside are going to come on when the door is open, and they're going to be off when the door is closed. The light module needs 120 volts to work. So if this switch was angled down that way, we wouldn't be getting voltage there. So in this configuration, the door is open, light's getting energized, and our control board is seeing that the light or the doors is open. Now, if we take a look at like a brand new unit, and this is a newer GE diagram we've got here, rather than mechanical switches, kind of like this, letting the door board know that, things like that, and you can kind of see in this diagram, line voltage comes over directly to the light module. On newer units, you're going to see more sensory inputs than you are mechanical action, kind of like this. And what I mean by that is, let's take a look at the defrost circuit. Now, if you take a look at it, kind of drew it out here, got a thermal fuse there. It branches off into a parallel circuit for the fill tube heater and the defrost heater. And then neutral comes back, another thermal fuse here, and back to the board. There's no bimetal on this, if you'll notice that. You do have two thermal fuses. Now, one of the things to keep in mind, when you see thermal fuses, they're one-off fuses. They're not going to open and then close. So when you're looking at something like this, there's no mechanical switch in the circuit, so to say, like a bimetal. You just have fuses, and it's kind of called out there, fuse. opens at 77 degrees Celsius or 170 degrees Fahrenheit. So if it gets hotter than 170 degrees, that pops and you're not going to get any heat. Now, the question is how does the control board know what the temperature is in there? What the temperature is? How does it, dictate that? Well, if we come over here, we've got a thermistor evaporator. On newer units, you're going to see this more and more often. You're going to see an evaporator thermistor in place of a bimetal. These offer a lot more precision, if you will, and there's a lot more information that the control board can get when it can see the exact temperature of that evaporator rather than, just whether or not we're getting, 120 volts or not. So that's something to keep in mind as well. And on a lot of the units, the defrost heater itself, the control board logic, if that thermistor is showing, let's say it's over 60 degrees Fahrenheit, most of the time it's not going to energize that heater circuit because it's too warm in there. And, the thought process behind that might be, hey, if the evaporator is 60 degrees, everything's going to be melted. There's no need for heat. In fact, it's not safe to initiate the heater. So, of course, if for whatever reason the evaporator thermistor fails, you've got these thermal fuses wired in series with the defrost heater as pretty much just a redundancy. And then one final thing, if you're looking at this, we got our AC voltage coming in. Let's assume this is our line voltage. Comes in, comes down, branches off to the ice maker. So on this one, looks like a standalone ice maker. It gets 120 volts, makes its own decision. But it also branches off and comes down here, branches off again. We come right over here, freezer door switch. Comes over here, branches off 2 times more, so it looks like it's got 3 door switches that are going to make some motion on this. But if you'll notice, unlike over here, where these are directly into the board, where these are directly to the light module, with this one, it's just going straight to the board. There's no lights in here. So what that indicates is that the board is just using the door switches, 120 volts being present there, for sensory purposes. And what it'll do when it sees 120 volts, if that door's open or closed, just depending on which layout this is, it's going to turn on the lights. It might turn off the cooling and do other things like that. So control systems use sensory input devices to make decisions. You can see what sensory inputs a control uses by looking over the schematics, and oftentimes in the technical documentation, if you actually take the time to read through it, like the service manuals, they'll tell you most of the time. You can use these sensory inputs to make checks on the control board rather than completely disassembling to access the components. And what I mean by that is, let's go back up to the bimetal. If you access the control board, let's say you have a completely frosted over defrost. If you access the control board and you disconnect this connector, if you get a resistance reading from this line to this line, it's going to show you if our defrost circuit, or at least the bimetal, if it's open or closed. We don't have to steam the whole unit out to access that to make a check. You can make it right from the control board. Minimal disassembly, and you're saving a whole bunch of time. And then conversely, let's say the bimetal's closed. Okay, well, maybe we want to check the defrost heater. I still don't want to steam the whole unit out to get to it. Well, take a look at this. If we instead take this line right here, it circumvents the bimetal, comes through the defrost heater, and then let's just say, look at this. We come down this way, we trace it out, and look at this. Comes right back up to there. So if we were to take a resistance reading with this disconnected from the board from this pin to this pin, that's going to isolate our defrost heater, and we can see if it's open. There have been times where I go out to a unit, not defrosted, completely iced over. Instead of completely steaming it out to make that check, I just check right from the board, and I find that I've got a good defrost heater, I've got a good bimetal. Well, guess what? That leaves the control board. You can take a jumper wire, because we can see line voltage comes in right here, right to there. We can put a jumper wire from right there to right there. If our heater circuit is energized, then guess what? Your control is either not sending voltage, or you got an issue with the thermostat where it's not letting it know that cooling's satisfied, so it just keeps cooling. Those are some diagnostic steps you can take. And this is one of the things I keep talking about. Isolating your problem, so that way we're not, focused on all the other wires, and B, making your checks from the board. I still talk to techs all the time who, have the whole unit defrosted. They spent 15, 20 minutes steaming it out. Defrost heater checked good. This checked good. Make your checks from the board. It's not that difficult. I mean, see right there? And it's really simplified when you've got the lines going through it, but there, you got that there. So let's go find this last slide. Some control systems do allow you to change from adaptive defrost to time defrost. You're going to have to refer to the technical documentation for that. If your defrost heater is working, you're just seeing a little bit excessive buildup, then it might be a good idea to try to change it to time defrost. And then regardless of new or old units, control systems rely on sensory input devices to make decisions. When you're facing an issue, you need to know how the system as a whole works to properly diagnose it, or else you're just going to be throwing parts at it. If you like this training, head on over to ApplianceTechAcademy.org. We've got a great training program and a whole bunch of other content and useful tools for you as an appliance technician.